Hi, in this video we will be discussing about cache optimizations for SAT solvers. Our aim is to experiment with different cache inclusive policies and cache replacement policies and evaluate them for different SAT solver traces to improve the cache performance. A cache level is related to the previous or the next level depending on which data blocks each level contains. Here by lower I mean L1 is lower to L2 and L2 is lower to LLC. Each cache level can use a different inclusion policy. For example, L3 can be exclusive of L2 while L2 is inclusive of L1. First, we'll go through with the inclusive policy. An inclusive cache contains all data blocks of the lower level plus some other blocks. The popularity of inclusive LLC arises from the bandwidth advantage it offers and the simplification it allows to the cache coherence protocol. A processor receiving a coherence request would try to find out if the requested block is present in its cache hierarchy. If the LLC is inclusive and LLC lookup is a miss, there is no need to forward the request to the inner levels of the cache hierarchy. In this discussion, we will confine to a single core evaluation. A disadvantage is that effective size of the cache hierarchy is same as that of the size of LLC. This is due to the data duplication. Another disadvantage is back invalidations. Eviction from LLC can generate an invalidation in an L1. If it was present in the L1, the block may be in use. This can be a problem. Now the exclusive policy. An exclusive cache does not include any replicated block from lower levels. This policy increases the total amount of data blocks that can fit in the whole cache hierarchy. This is similar to a victim cache. In a three-level cache hierarchy, the LLC would be the victim cache of two-level cache. These caches contain the evicted block from the lower levels aiming to reduce conflict misses. The main benefits of this policy are higher effective space as it avoids block duplication in different levels and also the lesser conflict misses. One of the drawbacks is that implementation is a bit more complex than the other policies. We will be implementing these two policies additionally as the given function code already contains an INE policy. Now the cache replacement policy. These are basically algorithms that improve the cache management. When the cache is full, the algorithm chooses which block to evict to place a new one. So which block to evict from the cache then? The best would be to evict a block that will be used furthest in the future. As part of LabFi, we have already implemented the LFU, FIFO, and random replacement policies. We will evaluate the performance with the LRC policy as baseline. Yeah. Now I think Pranay can take over with the implementation part.
So we have already learnt the theory of inclusion and exclusion policies. Now we need to see how do we implement on the code. So uh, let's see the features. So where we should write our code in the cashier.cc. That's the first question. So what we learned is we need to implement some extra features other than already which are there in NINE. So the extra features are always implemented when we are removing a victim. So just what we'll do is we'll find where we have find victim function in the cashier.cc, and we'll add some new function below find victim which implements the extra functionalities of inclusive if it's inclusive, it's exclusive if it's exclusive. So we'll see the functions. So in inclusive implementation, I wrote a function named higher level dirty, which takes the address, which goes into the higher level and checks whether the given address is dirty or not. If it is dirty, what we need to store that data, and we need to send it to our lower level to preserve the data. So we have to call this function after every find victim, and after sending the packet, we should not forget to invalidate this data in higher levels. We should remove this because we know in inclusive L1 is subset of L2 is subset of L3. When we are removing from some cache, we need to remove them from higher levels also. Let's see the code implementation. So in inclusive, what we have saw is I wrote a function. Uh, I wrote a function where it is higher level dirty. It takes an address and it goes through the higher level. Here it gets the set and way. Here it goes to the higher level. It checks whether higher level is dirty. If it higher level is dirty, we'll just get the data from there and we'll do dot valid 0 in the higher levels. And here, if it is valid, what will if it is valid in our present data. I mean, if upper level dirty is non-zero, then only we'll come here. Otherwise, we'll return. If we come here, uh, we'll just see whether now it is dirty or not. If it is dirty, we'll return dirty. So this is our inclusive implementation. So in exclusive implementation, it is simple. We just take an address, see if it is dirty. If it is dirty, just send to lower level. That's it. So many times we forget to invalidate it from LLC when we do the read function. When we call a read from L1 to L2, so we forget checking that. So this is my code for exclusive. So this is a function exclusive. Just take the address, and if it is L2C and it is valid and it is dirty, we'll just send a packet to lower level. This is called after every find victim. And coming to our implementation, how do we know whether our implementation is correct? We'll just in if it is inclusive, L2 write back misses and LLC write back misses should be zero, because the write back packets come whether there is the right we send the write back packets if it is only present in the lower level. We need to update the value. So well, we are seeing for an update. So in inclusive, L1 is subset of L2 is subset of LLC. So there must be data. So there will be no misses. The misses will be zero. Whether in case of exclusive, it is present only at one place. If you are writing to the lower level, it will not be present in the lower level because it is already present in the upper level. So write back hits will be zero. So that's it about the implementation of the code. So next, Anjan will carry on with the graph details, graph and their results and inferences.
How do we infer? We infer from the data. Data is generated from three traces given, and three inclusion policies and four replacement policies. So we'll get 36 files. We also varied LLC certain ways, in four different ways. So we'll get 144 files, and we drew the data, and we plotted graphs. So for each trace, we'll compare policies of same size. From this, we'll take the best replacement policy and we'll plot three different graphs, and with different sizes for the best policy. Why is only LLC way varied over the graphs and why not L2C and or L1C? In the graph plotted, when we vary L2C, we do not see such an significant increase in the IPC value, uh, which is given by LLC. So we only changed LLC since it gives a significant increase in the IPC value. Which is the best cache inclusion policy for the given traces. Since SAT solver does random access of memory uh, by the graphs, we observed that there is a high IPC for inclusive compared to exclusive. So we infer that there is a high probability of high spatial locality than high temporal locality, since inclusive is best for high spatial locality and exclusive is best for high temporal locality. Which replacement policy works the best? FIFO. FIFO works best when there is a sequential alignment in memory accesses, which is similar to LRU. Uh, LFU does not work better here because there is no dependence of frequency of memory accesses, because the SAT solver doesn't depend on frequency of variables used already. So now we will so from these graphs, we can see that there is a significant increase in IPC values in cadical traces. Uh, so so KISSAT is memory efficient than Cadical, especially when dealing with large SAT traces. KISSAT is a class learning solver, which means that it keeps track of the classes that are necessary for solving the current problem. So CDCL, however, needs to learn, so it needs more memory. So we see there is an when we increase memory, there is an rise in IPC in Cadical than KISSAT. So KISSAT is memory efficient than Cadical. Why exclusive has higher miss rates? An exclusive policy means that a cache block can exist only in one level at the cache hierarchy at the same time. This means that if a cache block is evicted and is asked by the program, it will need to be fetched from the main memory, resulting in a cache miss. Whereas an inclusive policy allows a cache block to be present in multiple levels of the cache hierarchy at the same time. This means that if a cache block is evicted from the higher level cache, it may still be present in the lower level cache, reducing the likelihood of cache miss if it is needed again later. So we see a decrease in miss rates in inclusive compared to exclusive policy, and NIN is almost same as inclusive.
So what have we learned till now? We have learned the implementation of inclusion process and checking whether it's correct or not by seeing the write back hits in exclusive and write back misses in inclusive. And what is the compulsory condition for inclusive? L1 associative should A associative should be less than LLC. And why did we only change the LLC and not L2? Because we saw there is a significant increase in the IPC when they are changing LLC values because of random access of memory by SAT solvers. And what are the differences between KISSAT and Cadical solvers? The memory efficiency, and why the miss rates in exclusive are higher. We saw the reason. So these are our inferences what we got from the project. Maybe we are unable to explain in these 10 minutes you can view the slides and our data and our code. uh, and what we tried and but failed to implement is the latency and the LLC size empirical formula. We tried to change the size, and we want to change the latency as well, but we cannot get an perfect empirical relation. So we did not implement because we didn't get much of information about it. So there is we didn't get any function in the internet. So for others reference, I got a document in the internet where I used this. These contains all the information what we did. And thank you.